Welcome to a course on measure theory and integration. In this lecture, we are going to actually define what do we mean by a Lebesgue integral, and with which we'll work out few results. Right? This is the definition of a Lebesgue integral. Here, f is given to be some bounded measurable function. Okay. So here, as you people know, we are now dealing everything in the real line setup, right? So if you are given a function is bounded means what? Absolute of f of x has to be smaller than or equals m for some non-negative real number m, right? So it means minus m smaller than or equals f of x smaller than or equals m on a measurable set E. So which means for all x in E, this is happening to be true, and this function has to be measurable as well, right? So f is given to be a bounded measurable function on a set E with E being a finite measurable set, right? In this case, we define the Lebesgue integral of f over E as integral over E f of x dx is the infimum of simple functions, right? So this psi is a simple function here. In the previous lecture only we have proved this is same as that of supremum of integral phi of x dx over E for the functions f bigger than or equals phi, right? So like what we can have, if you have a simple, if you have any function, any bounded measurable function, you can identify a collection of measurable functions of this form, right? Take an infimum of this one and a supremum of fees. Okay, you'll have to take the supremum of fees and infimum of size. So in that case you would get something of this form, right? So integral is preserved. Okay, so this is what we'll have to do, right? Here the psi means, the psi means there are plenty of functions which satisfy this property, and we know how to integrate a simple functions. Once we integrate a simple function, that will give us some value and we'll have to take the infimum of all such values, right? And either you can define the Lebesgue integral with the help of infimum value or with the help of supremum value. If you are about to define with the help of infimum value, then you will have something like this. If you are about to deal with infimum values, sorry, for supremum values, here for all simple functions, this is happening to be for all simple functions, f bigger than or equals phi, right? So we can define Lebesgue integral in this form. Here let us note something, that is, if f is a bounded measurable function that vanishes outside a set E of finite measure, then integral over E f is nothing but integral f multiplied with characteristic function of E, right? We can write like this. So this is the note. Fine. So moving further, the first proposition that we have is if f is given to be a bounded function which is defined on a closed interval ab, and if the function is Riemann integrable, then this function is measurable and the Riemann integration is same as that of the Lebesgue integration. This is what we'll have to prove, right? So let us start the proof. Given f is a bounded function defined on this interval. Okay, suppose f is Riemann integrable on AB, then what do we get? We get upper Riemann integral and the lower Riemann integral are equal, right? So this is the definition of a Riemann integral. These two values are equal, and that is what we write it as Riemann integral of f of x. So let us mark this as equation 1. Now, what is our claim? So we'll have to claim this function f is measurable and Riemann integral is same as that of Lebesgue integral. Right. How are we going to prove this? So for which let us start with the result that every step function on a bounded interval, every step function on a bounded interval is a simple function. So hope you guys have the idea of what do we mean by step function, right? So if you just look at the definition of a simple function, you can very well see that is happening to be true. Here we are talking everything on a bounded interval. So bounded interval means bounded interval on a real line. So therefore the measure of that interval is its length. So when you can measure that, that is of course a measurable set, right? So once you have some measurable set, with that measurable set you can of course have a measurable function, right? So the step function that we define here is turning to be a measurable function, and it assumes only a finite number of values inside a bounded interval. So that is why it is a simple function. So once you have that simple function, then we can write lower Riemann integral of this quantity is smaller than or equals supremum of phi of x dx for, right? So this result we have seen while we recall few things about Riemann integration, that you can refer there, right? Okay, so supremum of this quantity is always what? Smaller than or equals infimum of this quantity psi of x dx, and this is smaller than or equals upper Riemann integral of f. Okay, so by equation 1 we conclude r of lower Riemann integral of f is same as that of upper Riemann integral of f, and that is same as that of supremum of phi smaller than or equals f phi of x dx, which is same as that of infimum of psi bigger than or equals f integral psi of x dx, right? So all these quantities are turning to be equal, and this is equal to integral a to b f of x dx, that is the Lebesgue integration. So this is by the definition of Lebesgue integral, right? So with which we have just proved Riemann integration and Lebesgue integration are equal. So that is Riemann integration is same as that of the Lebesgue integration. So we have claimed one result. Next we will have to prove, since supremum of phi uh, smaller than, just a minute. So I don't know what is happening here. Sorry for this. Since supremum of phi smaller than or equals f, just a minute. Here I'm not able to write. Okay, since supremum of phi smaller than or equals f, integral this quantity is same as that of infimum of psi bigger than or equals f, integral psi of x dx, they are same, we conclude that f is measurable. Okay, this is by the previous result that we have seen. So which completes the proof of the proposition. Right, I had one page but I urged everything. Okay, I gave you the entire proof in a single page. Okay, that's fine. Now let us move to the next result, that is the algebra of integrable functions. Right, so here you have f and g are some bounded measurable functions which is defined on a set E of finite measure. So if you just recall this thing, here f is a bounded function on some closed interval and all those things are there. Here you are given that f and g are bounded sets on a set of finite measure. You do not have any guarantee that E is equal to a closed interval AB. If you have E is equal to closed interval AB, then all these results, then you can make use of the ideology that all these results are true in the case of Riemann integration. Once this is true for Riemann integration and we just prove Riemann integration over this interval is same as that of the Lebesgue integral. So you can just incorporate all those results that are available for Riemann integration to this Lebesgue integration only when f is bounded, f is a bounded function on a closed interval AB. Right? So here what we are about to prove is true in much more general sense. Here we have a set E that has a finite measure. There is no guarantee that all the sets with finite measure are some bounded intervals, right? It may or may not be the case. This is a larger than the previous one. Okay, now let us get into the proof. Okay, if you see what is the first thing that we have, let us start the proof. Okay, what is the first thing that we have? F and G are bounded measurable functions and we'll have to talk about the integrals. So before getting into it directly, let me just do one thing. If some psi is a simple function, then what do I have? Then by the definition, psi is a measurable function first of all. And psi takes only a finite number of values. Right? If that is so, then what about AF? Right? So for any A non-zero, A psi is also a measurable function. And if psi takes the values alpha 1, alpha 2 till alpha n, then your A psi takes A alpha 1, A alpha 2, etc. till A alpha n. So clearly psi is, sorry, your A psi is also a simple function, and it is obvious that if ASI is a simple function, since A is assumed to be non-zero, you can take you can just multiply 1 upon A with this function to get psi is also a simple function. That is what we prove here is if A is a simple function, then so is ASI, and if ASI is a simple function, then so is psi. Okay, so that is what we have just proved here. Okay, now let us start. If A is some positive quantity, then integral of AF is nothing but infimum of phi smaller than or equals F. This is equal to A phi. Since A is a constant and is independent of this F and all, you can take this A outside. So what you will have is that infimum of phi smaller than or equals F, that is equal to what? Phi, and that happens to be A times of integral F. Right? Now let us do, if A is smaller than 0, then what happens? Then integral AF. Now remember, A is a negative quantity. So here when you take the just a minute, did I miss anything? Yeah, so in this case what should we have is that we must have, okay, there is no issue in taking a phi, but this phi has to be bigger than or equals F. Okay, so we can just revisit the definition of Lebesgue. See, when you take infimum, that simple functions that you take has to be bigger than or equals the original function. So it has to be of this form. Here, infimum of, you see, whatsoever the function that you take, that has to be bigger than or equals F. Right? So, but A is a negative quantity. So what we'll have is that we have the reverse inequality here. Right? So we'll have the reverse inequality here, and since this A is independent, so we take it outside. When you have that A multiplied with it, you had the negative sign, right? So having the negative sign, you are taking the infimum. Now you have taken that A outside, so you have taken the negative part outside, then you must take the supremum. So supremum of uh, supremum of psi bigger than or equals F, I suppose. Sorry, supremum of psi smaller than or equals F, and this happens to be what? Simply psi. So this is again equal to A times of infimum phi bigger than or equals F and integral phi, and that is simply integral AF. So in both the cases, that is for any A not equal 0, your integral AF is same as that of A times of integral F. Right? Now, let us consider if psi1 is a simple function such that psi1 smaller than or equals F, and psi2 is a simple function such that psi2 smaller than or equals G. If this is the thing that we are taking, then psi1 plus psi2 smaller than or equals f plus g. Okay, this is happening. Therefore, integral f plus g is bigger than or equals integral psi 1 plus psi 2. Since psi 1 and psi 2 are simple functions, we can split this into integral psi 1 plus integral psi 2. Okay, so this is true for supremum on the RHS. So that is, this is, we are saying that this is true for supremum on the RHS, which means uh, integral f plus g is bigger than or equals. First, if you take the supremum of psi 1 smaller than or equals f, and here this is independent of psi 1, so that does not affect this. And when you take the supremum psi 2 smaller than or equals g, that does not affect the first integral. So first let us take this one. Okay, first let us take this supremum. So this just affects only the first quantity. It will not affect the second one, so we just simply write this as integral psi 2. So and this is nothing but integral f plus integral psi 2. This is what you have. So next, if you take the supremum psi 2 smaller than or equals g to this integral, so this does not affect the first one, so we write it simply. And then supremum psi 2 smaller than or equals g integral psi 2, this is nothing but integral f plus integral g. So combining all these things, what we are having is that integral f plus g is integral f plus integral g. Sorry, we have bigger than or equals, we mark this as equation 1, right? So here we have taken simple functions of this form, and if we just take if phi1 is a simple, phi1 and phi2 are simple functions, such that your f smaller than or equals phi1 and g smaller than or equals phi2, then proceeding as above, by taking infimum, what we are going to have is that integral f plus g smaller than or equals integral f plus integral g. So we mark it as equation 2, right? So you will have to just do the same thing, right? So instead of greater than or equals, here you will have smaller than or equals. Instead of functions psi 1 and psi 2, you will have phi 1 and phi 2. Then you will have to take the infimum value. So the first, when you take the infimum, that will affect only the first integral, and the second infimum will affect only the second integral. So as a result, you are going to get integral f plus g is smaller than or equals integral f plus integral g. We mark it as equation 2. So by sorry, so from equation 1 and 2, we get integral f plus g is same as that of integral f plus integral g, right? So we just prove these two things are happening to be true. Now let me just mark this one as star and this one as double star. So by star and double star, integral af plus bg So first using double star, we split this as integral AF plus integral AG, and using star we split this as in A times of integral F plus B times of integral G. So this proves the first part of the proposition, right? So now we'll go to prove the second part. So in the second part, what is the hypothesis? That is the assumption that we take. So it is given that F equals G almost everywhere, right? So then what we have is F minus G equals 0 almost everywhere. Okay, this is happening. Then therefore there exists a simple function. Okay, there exist simple functions. There exist simple functions psi with psi bigger than or equals F minus G. Okay, since F minus G is 0 almost everywhere, this means your psi is bigger than or equals 0 almost everywhere, right? Then what? Your integral psi is bigger than or equals 0. So this means your integral F minus G is bigger than or equals 0. We mark it as equation 1. Sorry, we mark this as equation 3, right? So similarly, for simple functions phi with phi smaller than or equals F minus G. Okay, what we are going to have is phi smaller than or equals 0 almost everywhere. Then integral. So we previously got that phi is smaller than or equals 0 almost everywhere. Therefore, integral phi is smaller than or equals almost everywhere. Once you take the infimum or supremum correspondingly there, with this, how did we come to a conclusion? We just take. So if we have something of this sort, then we'll have to take the infimum value, right? So there are plenty of functions which satisfy this condition. Once we take the infimum value, we get this one. So from this we arrive the equation 3, and here when you take the supremum value, what you are gonna get is integral f minus g is smaller than or equals 0. So we mark this as equation 4. So by 3 and 4 we get integral f minus g is equal to 0, and take a to be equal to 1 and b to be equal to minus 1. In part 1 we get integral f minus g equals integral f minus integral g, which is equal to 0. So with which what we conclude is that integral f equals integral g. This is over the set E. Okay, here whatsoever the integrals that we are talking about, this is over a set E. That has to be clearly specified, right? So I forgot to specify that everywhere. So let me just do it now. Okay, you people have in your mind that we are talking everything over E, right? So we have all these things over the set E. Okay, I'll just complete it while before uploading the material to you people. So now let us move to the part 3 of this proposition. So in the part 3, what we assumed is that, so what we have is given f smaller than or equals g almost everywhere. Then f minus g, or you can write g minus f is bigger than or equal to 0 almost everywhere. The reason why we are choosing a non-negative function is that it is easy for us to work with non-negative functions than the non-positive functions, right? So we just have something of this form, right? So after having things of this form, there exist simple functions psi such that psi is bigger than or equals g minus f. So that tells us that integral psi of x is bigger than or equals 0. So which tells us that integral psi is bigger than or equals 0, and taking the infimum we write integral g minus f is bigger than or equals 0. Again using the previous thing, integral g minus integral f is bigger than or equals 0. That tells us that integral g is bigger than or equals integral f, and we were asked to prove what? Integral f is smaller than or equals integral g. So this is what we wished to establish. We should prove. Okay, let me just write down the claim since it is few pages before. The claim is to prove absolute of integral f is smaller than or equals integral absolute of f, for which we observe that integral. Okay, so I'm not doing it for integral. Let me just do it for what shall I say? Minus f is smaller than or equals absolute of f, right? And f is also smaller than or equals absolute of f, since f is a real valued function here. Okay, so this is happening to be true for all the functions that we are discussing. So we just proved that if we have this one, then this is true. So we mark this as equation 5, right? So by equation 5, integral minus f is smaller than or equals integral absolute of f, and integral f is smaller than or equals integral absolute of f. So the first one, we can just take this minus outside. So integral f smaller than or equals integral absolute of f, and we have this one. So integral f smaller than or equals. Okay. Now after you do the integration, what you have is that you have what? After an integration, that will give you some value, right? So these integral quantities are some values. You have minus a smaller than or equals b, and a which is also smaller than or equals b, which means your absolute of a has to be smaller than or equals b, right? So this is a result. So using that result, we just combine these things as absolute of integral e f is smaller than or equals integral over e absolute of f. Okay, so this actually completes the third part of this proposition. And in the fourth part of the proposition, what we are about to prove is that we are given that a smaller than or equals f of x smaller than or equals b. Okay, then we'll have to prove the claim is a times of measure of e smaller than or equals integral f of x. Okay, so integral f of x dx smaller than or equals b times of measure of e. Here a and b are some constants, right? So this is what we have. So in order to prove this, we have, since a smaller than or equals f, we have integral a smaller than or equals integral f, right? So here we know that, or we shall just deduce that integral over E 1. So what is this quantity? Right? So what is this? You just see, you can treat phi to be equal to 1. Actually your phi of x equals 1 for all x in E. Right? So in the okay, I'll have to do it in green color, right? Okay, if you just look at this set E, this is a measurable set. Why so? It is given in the hypothesis of the proposition itself, right? This is a measurable set. Fine. Your phi just takes a finite value. Only one value it is taking, right? So it is taking this one. So when you wish to write this in that form, that is using the help of a characteristic function, you just write your phi of x to be 1 multiplied with chi e, right? Suppose if it is taking, instead of 1, if it is taking some other constant a, so this is what we are going to write. Okay, and what is the integral of these type of functions? That is integral over e is nothing but a, this one. Since a is a constant, we take it outside. So integral of a characteristic function is nothing but the measure of that set e. So this is what we are going to have. Fine. So using that ideology, okay, but integral over e a is nothing but a multiplied with measure of e, right? So a measure of e is smaller than or equals integral over e f. So we mark this as equation 6. So from the given information, we broke that one into two parts. A smaller than or equals f of x that we have taken, and with that we deduced this equation 6, right? Similarly, with the help of sorry, yeah. Similarly, f of x smaller than or equals b. This gives us integral over e f of integral over e f is smaller than or equals b times of measure of e, right? So we mark this as equation 7. So from 6 and 7, a measure of e is smaller than or equals integral over e f, that is smaller than or equals b measure of e, right? So now we'll prove the last part of this one, that is given a and b are disjoint measurable sets of finite measure. So in this case, let us see what is the characteristic function of A union B, right? So if you just look at the characteristic function of A union B, this takes the value 1 if x is a member of A union B, and 0 if x is not a member of A union B. If x is not a member of A union B, it means what? X is not a member of A and x is not a member of B, right? If it is not present in both the sets only, it is not present in the union as well. Okay, now this means what? Either x has to be in A or x has to be in B. Sometimes it can be in both, but here we are clearly given that A and B are disjoint sets, so it cannot be present in both the sets. So these are the possibilities, right? So now if you just see, okay, let me take the case when x is a member of A. When x is a member of A, it clearly tells us that x is not a member of B, right? So then chi A of x is nothing but 1 0 if x is a member of A and x is not a member of A. Okay, so and your chi b of x is nothing but is 1 if x is a member of B and 0 if X is not a member of B. Right? So this is for the case when X is a member of B and X is not a member of A. So if you just add these two things, what are you going to get? So actually in these cases, if X is member of both A and B, can it happen? It cannot happen at all, right? So either X can be X is a member of A. If X is okay, I think this part is not visible to you people. So let me just write here. You have chi A of X plus chi B of X. So let us check the case. When X is a member of A and X is a member of B, this cannot happen at all, right? So this is not applicable here. And when X is a member of A and X is not a member of B, so in this case from here you will get 1 and from here you will get 0. So the resultant is 1. And when X is X is not a member of A and X is a member of B means, so from the first one you will get 0 and from the second one you will get 1. When X is not a member of A and X is not a member of B. So this can happen, right? So when X is not a member of A we get 0. When X is not a member of B we get 0. So 0 plus 0 is this one. So we just shall combine this as chi A of X plus chi B of X is equal to 1 if X belong to A or X belong to B, and 0 if X is not a member of B and X is not a member of A. Okay, in these cases we get this one, right? So this is exactly same as that of the chi A union B. So this can happen. Remember, this can happen only when A and B are disjoint measurable sets. Okay, they must be disjoint. What if the disjoint is not there? It means here you will have your X can be in A and X can be in B. Okay, so in this case, when X is a member of A and as well as when X is a member of B, in the place of not applicable, you will get 2. This is no more a characteristic function, right? We must have a characteristic function. So that is why when we have two uh, measurable disjoint sets, what happens? That is what we are dealing here. So this is nothing but your chi A plus chi B, right? So we have this one. Now let us do integral A union B f. So it is what? It is integral f multiplied with characteristic function of this A union B. So this is integral f characteristic function of A plus characteristic function of B, and when you multiply this one, this is using the property 1 of this proposition. We have this quantity, right? These are chi. This is nothing but integral over A to the function f, and this is integral over B to the function f, right? So finally what we have is integral A union B f is integral over A f plus integral over B f. So this completes the proof of the proposition. Remember, this can happen only when the disjointness is there. If we remove the disjointness, this cannot happen. If we remove the measurability, of course this cannot happen. So